Welcome back to the deep dive. Today we are taking a massive leap into the world of Apple's declarative framework, SwiftUI.
Yep.
Introduced back in 2019, right? And this technology, it just fundamentally changed the relationship between the developer and the UI.
Totally. It really did.
So we're not just going to, read the docs here. Our mission today is to really tear down the architecture. We want to understand the core differences from the old way, UIKit.
Yeah, understand state management properly.
Exactly. Master that intricate state management system and maybe decode some secrets to getting really robust performance out of it.
I think that's a good plan. It's definitely an essential deep dive if you're aiming for, let's say, mastery, not just basic competence.
Right.
Our goal here is basically to provide that architectural roadmap. We want to move beyond just simple definitions and really explain the critical why behind SwiftUI's design choices.
Okay, let's start with that big shift, that seismic shift in philosophy. If you're coming from UIKit, you lived in, an imperative world. We need to define clearly what this SwiftUI declarative thing actually means in practice.
Okay, so in the imperative world, UIKit, you, the developer, you were responsible for managing every single step of the process for the UI.
Mm-hmm.
You told the system how to do things.
Yeah.
Right? How to make a button, how to position it, how to handle the tab.
And crucially, how to update the view when data changed.
Exactly. Critically, how to manually update it. You'd call explicit layout methods like set needs layout, or maybe even worse, you'd directly mutate properties on a view object, probably on the main thread, hoping for the best.
Which meant a huge cognitive load, right? You were constantly fighting state inconsistencies, debugging race conditions, layout bugs, maybe just because you forgot one little manual update call somewhere.
Precisely. It was brittle.
Yeah.
So the declarative approach flips this entirely. With SwiftUI, you just describe what the UI should look like, based only on the current state. You declare the end result, the what. The framework itself, specifically the SwiftUI rendering engine, it takes over all the heavy lifting. It figures out the smartest, fastest way to transition the UI from, say, state A to state B.
So the developer's job becomes managing the data and describing the appearance.
Pretty much. Manage the data, describe the look. That's it.
So if I change like a single Boolean in my data model, I don't touch the view directly. I just trust SwiftUI to see that state change and boom, automatically synchronize the UI.
Exactly. That's the promise. And the power isn't just, conceptual, it's practical. That single code base now supports iOS, iPadOS, macOS, watchOS, tvOS.
Which is huge.
It's massive. And the immediate feedback loop you get with Xcode's live preview, that made the development process instantly more, tactile and efficient. It cut down dramatically on that painful compile run debug cycle we all used to suffer through.
Yeah, that wait time was killer. Okay, before we jump into the structure, just a quick note on the entry requirements. SwiftUI launched with iOS 13.0. That's true.
But yeah.
If you want access to a lot of the really critical performance and navigation features, we'll talk about things like lazy containers, the navigation stack, that task modifier. You really need to be targeting, iOS 15 or 16 and later?
Yeah, I'd say 15 minimum, ideally 16 plus my card. The framework has matured a lot since its debut. It's much more capable now.
Right. That continuous evolution is key. And it brings us, I think, directly to the foundational building block that actually enables all this declarative efficiency.
Okay, so here's maybe the first architectural insight that really surprises people coming over from UIKit.
Lay it on us.
In UIKit, views like UI View, UI View Controller, they were heavy classes, reference types right now. They persisted in memory, and developers had to manually manage their memory, their complex lifecycle.
Oh yeah, retain cycles, anyone.
Exactly. SwiftUI views, though, are defined as structs, value types. And this shift from reference type class to value type struct, it's profound.
Brother, why? Why is that so fundamental?
It's probably the single most important architectural departure. Structs are value types, meaning when their underlying data changes, you essentially get a whole new copy.
Okay.
This makes sure they're lightweight, super easy to recreate, and, crucially, predictable. Because they're so cheap to create, SwiftUI doesn't even try to mutate some persistent view object. Instead, when the state that drives the view changes,
it just recreates the whole view struct.
It just recreates the view struct entirely, throws the old one away, makes a new one based on the new state.
But wait, doesn't recreating the entire view structure sound incredibly inefficient compared to, just changing one little property on a UIKit view object?
That's the common misconception. But it's actually the brilliance of the declarative approach combined with these value types. Since the structs are so lightweight, they basically just contain a description of the UI, not the rendered pixels or heavy state. Recreating that structure is extremely fast.
Faster than patching properties?
Way faster, generally, than manually patching properties on some persistent, potentially complex object. Especially when you factor in the memory overhead and management complexity of those old UIKit object hierarchies. Views defined as structs, they don't hold state themselves, remember?
Right, they read external state.
Exactly. They are simply blueprints. Blueprints for the current visual representation based on the current state.
So the developer provides the blueprint. SwiftUI's rendering engine takes that blueprint, constructs the necessary UI elements, and this gets rid of those memory-heavy view controllers we used to wrestle with.
Pretty much. They're transient snapshots. They don't persist in memory unless you explicitly reference them somewhere else, which lets the system be really aggressive about efficiency and reconstruction.
Okay, that makes sense. Now, if views are constantly being recreated, we often need to define complex layouts, right? Like maybe combining 3 text fields, 2 buttons, an image, all inside a VStack. If we just wrote that out naively, Swift would probably force us to wrap those individual views in like an array or something, which would make the code look awful, unreadable. How does Swift UI avoid that structural nightmare?
Good question. That's where View Builder comes in. It's absolutely essential for that clean, nested syntax we all rely on. View Builder is a special function builder feature in Swift itself.
Okay.
It lets a closure, like the content block you pass to a VStack or an HStack, or even your custom view's body property. It lets that closure return multiple views implicitly without you having to wrap them manually.
So like under the hood, I just type 5 lines, each defining a view inside my VStack braces.
Yeah.
And the View Builder compiler magic automatically combines them into a single cohesive view structure. It handles the wrapping.
That's spot on. It streamlines composition, makes the code highly readable, and if you're creating a custom function or maybe a computed property that needs to return several views combined, you just slap the Add a View Builder attribute on it, and the compiler knows exactly how to combine those separate view declarations into one coherent structure for you.
Nice. Okay, let's shift gears a bit to the view lifecycle. In UIKit, our anchor points were obvious, right? View did load. Okay, the view's in memory. View will appear, it's about to show up.
The classics.
Since SwiftUI views are constantly being destroyed and recreated, how do we hook into those kinds of events? Is there a view did recreate or something?
No. You don't have explicit lifecycle methods like that because the entire lifecycle is fundamentally state-driven. The core mechanism is always. State changes, view gets recreated, body property gets reevaluated. That's the loop.
But I still need to do stuff when a view appears on screen, right? Like maybe start an animation or fetch some initial data.
Absolutely. Yeah. And for actions tied specifically to a view appearing or disappearing, you rely on modifiers, specifically on appear and on disappear.
Okay.
So for instance, if you want to log something or maybe set the initial focus on a text field when the view shows up, on appear is the tool for that job.
Gotcha. This brings us to a really crucial point, especially with modern concurrency. Since Swift got async await, I see the newer task modifier being used everywhere for data fetching.
Yeah, it's become standard practice.
And I've definitely seen developers try to use onAppear for network calls and run into, well, problems. What's the fundamental difference there, especially when dealing with async work?
This is a vital distinction. Really important for efficiency and preventing resource leaks. onAppear is meant primarily for, let's say, synchronous setup tasks, or maybe initiating processes that you might need to manually cancel later on disappear.
You can call async code in it though, right?
You can technically call asynchronous code from within onAppear. But if you do, you are responsible for managing the lifecycle of that async task yourself. You have to handle cancellation if the view disappears while it's running.
Right, okay. So task.
The task modifier, which needs iOS 15 or later, is explicitly designed to work with modern structured concurrency. When you attach .task to a view, you're telling SwiftUI, hey, start this asynchronous task like a network fetch or some heavy calculation when this view appears.
And the crucial part.
The crucial part is the system automatically handles the cancellation of that task when the view disappears.
Oh, wow, okay. That automatic cancellation is a huge win for robustness.
Huge.
I remember spending hours in UIKit making sure I properly nilled out delegates or canceled URL session tasks and view will disappear or dean it just to avoid memory leaks or like ghost data updates happening after the screen was gone.
We've all been there.
The task modifier sounds like it just solves a whole class of those concurrency management problems automatically.
It genuinely does.
Yeah.
It ensures that when your user swipes away a screen or navigates back, the system stops that background work immediately, saves battery, ensures clean memory management. It's much safer.
Okay, this leads us perfectly into the absolute core engine of SwiftUI state management. If views are just these transient things being constantly recreated, then the state, the actual data, must live outside the view structure itself.
Exactly, which mandates adherence to the single source of truth principle.
Right. Single source of truth. Let's unpack that.
Yeah. The whole declarative paradigm basically falls apart if your data is duplicated or inconsistent.
Yeah.
Single source of truth just means there's one canonical, authoritative place for every piece of data that drives your UI. One source.
And all the views just read the live value from that single source.
That's the idea. They observe it.
And the practical benefit seems enormous. You avoid those nasty data inconsistencies. You simplify the flow of information through your app.
And debugging becomes dramatically simpler. Because if a piece of the UI looks wrong, you know exactly where the data came from. You look at the single source.
Yeah, you're not chasing down 5 different potential sources for the same label text.
Right. It also allows for extremely clean control flow for showing or hiding things. Because views are value types, doing conditional rendering is just standard Swift syntax. You use if-else blocks or ternary operators directly inside the body property.
So no more manually adding and removing subviews or setting is hidden flags.
Nope. You just describe the structure if the state meets a certain condition. If the condition is false, that part of the structure just isn't included in the blueprint SwiftUI generates.
Clean. Okay. And the mechanism SwiftUI uses to actually establish and enforce this single source of truth. That's the property wrappers, right? At state, at binding, etc.
Exactly. These are the tools. The property wrappers link data changes to UI updates. They're the glue. Let's start with the most basic, most granular level, local view state. That's handled by at state.
At state. Yep.
At state is for simple, private data that's local to a single view and really only affects that view.
Like what? Give me an example.
Think about data with, like, fleeting relevance. Is a toggle switched on or off? What's the current value of a counter? Maybe the text typed into a local search field before you hit submit, that kind of stuff.
Okay, so the view owns the state's storage, but how is that storage actually persisted if the view struct itself is constantly being recreated? You said the structs are thrown away.
That's the magic of the property wrapper itself. When your view declares, say, at state var counter equals 0, SwiftUI does something clever. It allocates a dedicated piece of storage outside of the view struct managed by the framework specifically for that counter variable.
I see.
So when the view struct gets recreated later, the at-state property wrapper inside the new struct just reconnects to that existing storage location SwiftUI set aside earlier.
So the wrapper finds the persistent storage.
Exactly. This ensures the value persists across view recreations. But crucially, when you change the value through the wrapper, like counter +1, it signals SwiftUI, hey, my underlying value changed, which triggers a reevaluation of the view's body.
Okay, makes sense. Quick caveat, though. At state is for ownership within that view's lifecycle. If the view itself is completely destroyed, like you navigate away from that screen entirely, then that state storage is released, right?
Precisely. It's tied to the view's identity and presence in the hierarchy. Now, what if a parent view owns a piece of state using at state, but a child view down the tree needs to both read that value and also modify it?
Right, like a custom slider component.
Yeah. Passing the at state variable directly down would kind of break the encapsulation and ownership model. The child shouldn't really own the parent state.
So that sounds like the classic use case for at binding.
Bingo. At binding. It establishes a two-way connection. Think of it as a read-write link or a reference to a value that's owned somewhere else, usually by a parent view set state.
So the child view declaring it at binding does not own the data?
Correct. It does not own the data. It simply holds a reference, a binding to the parent state variable. When the child view updates the value through its binding.
It updates the parent's state.
Immediately. The change propagates back up to the source of truth, the parent's state. And because that state changed, the normal SwiftUI update cycle kicks in, synchronizing both the parent and child views and anything else depending on that state.
Okay, so at binding is absolutely essential for creating reusable components like custom form elements or controls. You declare the source of truth data in the parent using its state, and then you bind it to the interactive parts in the child view.
Couldn't have said it better myself. But now, what if we move beyond simple local state or parent-child binding? What about more complex, potentially shared data, like maybe an application user profile or data fetched from a network or a database? We need a different mechanism for that.
Right, something that can handle reference types and maybe notify multiple views. That brings us to observable object.
Exactly. Observable object is a protocol you apply to classes reference types, which are generally more suitable for handling complex, potentially long-lived data models. Think view models, data managers, that sort of thing.
And just conforming to observable object isn't enough, right? How does SwiftUI know when something inside that class actually changes?
Good point. To make SwiftUI aware of changes within that observable object class, any properties whose changes should trigger UI updates must be marked with another property wrapper, @published.
@publish, okay.
@published automatically synthesizes the necessary Combine publisher code. So whenever you assign a new value to a @published property, it automatically broadcasts that change via its underlying Combine publisher.
I see. So @publish makes the property observable. Now, this is where I think developers often hit a bit of a wall trying to figure out ownership and lifecycle when using these observable objects in their views. We have two key property wrappers for observing them, @stateObject and @observedObject. What's the rule of thumb? How do we choose?
Okay, yeah, this is a super common point of confusion, but the decision boils down entirely to two things.
Yeah.
Ownership and lifecycle. Who owns this object and whose lifecycle should it be tied to?
All right, let's start with @stateObject. When do I use that?
You use @stateObject when a specific view needs to create and own the observable object. Think of a root view for a feature, or maybe a main screen. That screen is responsible for initializing and managing the lifecycle of the view model that supports it.
Okay, creates and owns. What's the key benefit?
The crucial benefit is persistence. @stateObject ensures that the observable object instance it creates stays alive and persists its state even when the view's body gets recreated multiple times due to parent state changes or other updates.
So it survives the view struct recreation.
Exactly. If you didn't use @stateObject in the view that creates the object, that object could be unexpectedly destroyed and recreated every time the view redraws, leading to data loss, state resets, or maybe needless network refetching.
Right. So what's the common misuse of @stateObject then? Where do people go wrong?
Putting it in a child view,
Yeah.
a view that receives the model from its parent. If you mistakenly use @stateObject in a child view that gets past the view model, every time the parent view re-renders and creates a new instance of that child view struct, the child might inadvertently call the @stateObject initializer again, creating a brand new, fresh view model instance. It throws away the old one, loses any unsaved work, maybe cancels ongoing fetches. It's a massive performance and data integrity trap.
Ouch. Okay. Which is why we use @observedObject in those child or intermediary views that don't own the object.
Precisely. You use @observedObject when the view simply receives an already existing observable object instance from somewhere else, usually passed in its initializer from a parent.
So it observes but doesn't own.
Exactly. The view observes the external object, takes no responsibility for its creation or its lifetime. It just registers itself to be notified whenever that object's published properties change, so it can update its own UI accordingly.
Okay, summing that up. @stateObject is for the view that creates and owns the observable object, guaranteeing its persistence across view updates. @observedObject is for views that receive and observe an object owned by someone else.
Perfect. Got it in one. Now, finally, there's one more scenario. Data that truly needs to be shared almost globally across the app. Things like a theme manager, maybe the current user session details, or authentication status.
Right, data that many unrelated views might need access to deep down in the hierarchy.
For that, we use @environmentObject.
This helps us avoid that awful prop drilling, right? Where you have to manually pass an object down through like 10 layers of nested views just to get it to the one view at the bottom that actually needs it.
Exactly. Prop drilling is tedious and error-prone. @environmentObject provides seamless access across the view hierarchy. You inject the shared observable object high up in the view tree, usually near the root of your app, or a major section using the .environmentObject modifier.
You inject it once at the top.
Yep. Then, any child view, no matter how deep, can declare it using the @environmentObject property wrapper, like environmentObject var session, user session. SwiftUI automatically finds and provides the correct instance from the environment.
That sounds incredibly convenient. Is there a catch, a safety rule?
There is one critical safety rule. If you declare an add environment object in a view, an instance of that exact type must have been injected somewhere up the hierarchy using environment object.
What happens if it's not there?
If SwiftUI looks for it in the environment and doesn't find it, your app will crash at runtime. Kaput.
Ouch. Okay.
So it's a powerful tool, very convenient, but it requires careful planning about where you inject your shared objects.
All right, we've covered how to manage the data, the state, the single source of truth. Now let's dive into what actually happens when that data changes. This sort of invisible process of comparison and update. This is where SwiftUI really shines, right? Thanks to its diffing algorithm.
Yeah, the entire system is fundamentally built on this efficiency. When a property wrapper, like atState or atObservedObject, detects a change and triggers an update, SwiftUI doesn't just, start blindly redrawing everything on screen. No. First, it calls the body property of the affected view, or views. This generates a brand new view tree, remember. Just the lightweight blueprint describing what the UI should look like now based on the new state.
Okay, get to the new blueprint, and then the diffing process kicks in.
Correct. The rendering engine takes this new view tree blueprint and compares it very efficiently with the blueprint from the previous render cycle. It analyzes the structure, the types of views, and critically, the identity of each view element.
And it figures out what actually changed.
Exactly. It identifies the minimal set of differences. And only the parts of the UI that have genuinely changed are then actually updated or rendered on the screen. Everything else is left untouched.
How does SwiftUI efficiently track which views are like the same view between the old tree and the new one, especially in dynamic lists?
Identity is key here. For static views you just type out, it usually uses implicit identity based on the view type and its position in the structure. But for dynamic collections, things generated by for each or rows inside lists, providing an explicit identifier is usually mandatory.
This is why the identifiable protocol is so important in SwiftUI.
Absolutely fundamental. Conforming your data model to identifiable or providing an explicit id key path to for each gives SwiftUI a reliable, stable key to track specific data items across state updates.
So it can match things up.
Right. If an item's ID is the same in the old and new state, SwiftUI knows it can likely reuse the existing view container and just update its contents. If an ID disappears, it destroys the view. If a new ID appears, it creates a new view. If the ID changes, well, it usually means destroy the old, create a new.
So failing to use identifiable correctly or maybe providing unstable IDs that change unnecessarily means SwiftUI has to destroy and recreate views constantly.
Yes, and that's a major performance killer, especially in long lists or grids. You lose all the benefits of efficient reuse.
Got it. So the big picture implications of this whole declarative diffing approach are automatic updates, less potential for coding errors,
and inherently lightweight views. But this efficiency relies on us, the developers, structuring our data and views correctly, using identifiable, avoiding unstable IDs.
And avoiding common performance traps. Like what happens if I accidentally put some really heavy computation inside my view's body property?
Oh, that's a classic performance pitfall. Since the body property can be called very frequently, potentially hundreds of times during rapid state changes like animations, or even just scrolling, placing heavy data processing, complex calculations, or expensive function calls directly inside body is catastrophic for performance. It'll kill your frame rate.
That's the rule.
The rule is simple. Keep your body property lean and mean. Pre-compute data outside the view body. Do it in your view model, maybe in helper function call from onAppear or .task, maybe using a lazy property. Just get the expensive work done elsewhere. Then, simply reference the final result in your view body. The body should just describe structure and read pre-computed values.
Okay, pre-compute outside, reference inside. Got it. Let's talk about scalability and layout. If I need to display a really long, complex list, say, thousands of items, a regular VStack or HStack is immediately out, right? Because it renders everything up front.
Absolutely out. A standard VStack inside a scroll view would try to create and render all 1,000 views immediately, regardless of whether they're visible on screen. That would almost certainly crash your application due to memory pressure.
So what's the solution for large data sets?
You must use lazy loading containers. For scrollable lists or grids, we primarily have two families of options, list and the lazy stack grid family. Lazy VStack, lazy VStack, lazy VGrid, lazy grid, which came in iOS 14.
Okay, list versus the lazy containers. What's the defining difference? When do I choose which?
List is basically SwiftUI's direct equivalent of UIKit's UItable view. It's inherently scrollable, it handles cell reuse automatically and very efficiently behind the scenes, and it offers lots of built-in styling and features separators, row selection highlights, swipe actions, inset group styles, etc.
So if I need a standard-looking table view,
If you need a standard table layout with common iOS features, List is often the easiest and potentially most performant choice because it's highly optimized for that specific use case.
okay, and the lazy stacks and grids.
The Lazy V Stack, Lazy H Stack, and the Lazy Grids are designed for more custom layouts within a scroll view. Their key feature is that they load and render their content lazily. They only create the view instances for items that are currently visible on screen, or maybe just about to become visible.
So they're memory efficient for huge data sets.
Exactly. If you need, say, an infinitely scrolling social media feed with highly varied card layouts, or a complex grid that doesn't look like a standard table, a Lazy V Stack or Lazy H Grid inside a scroll view is likely the better choice. It gives you much more control over the individual item layout while still maintaining that crucial memory efficiency.
It sounds like Lazy V Stack and Friends are the way to go anytime the standard list styling and behavior feels too restrictive.
That's a good rule of thumb. But one important caveat. Be very careful not to nest scrollable things unnecessarily. Like, don't put a list inside another scroll view or a scroll view containing a Lazy V Stack inside another scroll view.
Why not?
Because it can often break the intrinsic size calculations and interfere with the lazy loading behavior. You might end up accidentally forcing the inner container to render all its content at once, completely defeating the purpose of using a lazy container. Keep your scrollable hierarchies flat.
Good tip. Okay, we've covered efficiency. Let's make things look good now. Animations. SwiftUI seems to handle animations, even complex ones, almost implicitly sometimes, often with way less code than UIKit.
Yeah, animation is definitely one of SwiftUI's strengths. The system supports two main approaches: implicit and explicit animation.
Implicit first.
Implicit animation is when you apply the animation modifier directly to a view or a container. You basically tell SwiftUI, hey, if any of the animatable properties of this view change, like offset, opacity, scale, color, I want you to animate that change using these parameters.
So you set it up once.
You set it up once, and then whenever a relevant state change occurs that affects that view, the animation happens automatically. It's kind of the fire and forget method for ensuring smooth visual continuity.
Okay. But what if I want more control? Like maybe I only want an animation to happen when I tap a specific button, but not when some other unrelated state changes.
Right. For that level of control, you use explicit animation. You wrap the state change itself with the animation block.
Ah, you wrap the action, not the view.
Exactly. This tells SwiftUI specifically, the state variables that are changing inside this block should be animated according to these parameters.
Yeah.
Any state changes outside the block happen instantly. This gives you much finer control over when animations occur, perfect for triggering them from specific user actions like button taps.
Makes sense. No, for those really impressive, almost magical UI sequences, like smoothly transitioning an element from a small image in a list into a big hero banner on a detail screen. That's matched geometry effect, right? What's the magic there?
Match geometry effect. It's incredibly powerful, and yes, it can feel like magic. It allows SwiftUI to visually track the geometry, that's the position, size, and shape of a specific element across two entirely different views, even if they exist in different parts of the view hierarchy at different times.
How does it track them?
It requires two key ingredients. First, you need a common namespace variable. You create this using @namespace and pass it into both views. This namespace provides like a shared coordinate space for tracking elements.
Okay, shared namespace. What's second?
Second, you need a shared unique identifier, IG, applied via the match geometry effect id.enat_isource, modifier to both the source view, for example, the smallest image, and the destination view, example, the large detail banner. This ID tells the effect which two views correspond to each other.
So namespace plus shared ID, then what happens?
When the state changes trigger the transition, example, navigating from the list to the detail, SwiftUI sees these two views with the same matched geometry ID in the same namespace. It intercepts the transition and automatically calculates and interpolates the frame, position, and size changes between the source and destination views, creating that seamless, fluid visual morph.
Wow, so it effectively fakes the appearance of one single view morphing and moving, even though it's actually two completely separate view structures being swapped out?
Precisely. It abstracts away all the incredibly complex manual coordinate space conversions, timing, and animation curves that used to make custom view controller transitions such a nightmare in UIKit. It's a huge productivity booster for polished UIs. But moving on to navigation. Mastering SwiftUI navigation is vital, partly because, honestly, it's been one of the most rapidly evolving areas of the framework since day one.
Yeah, the early versions were tricky.
They had their moments. So we really need to focus on the modern standard, which, since iOS 16, is the navigation stack.
Right. Forget the old navigation view. I remember the frustrations with that, especially unpredictable split view behavior on iPad and nesting issues causing weird bugs. Why did Apple move to navigation stack? What was the core problem with navigation view?
Well, navigation view's primary architectural flaw, looking back, was its heavy reliance on the environment and its, frankly, difficulty in supporting reliable programmatic navigation.
Yes. Trying to push views based on state changes.
Exactly. If you wanted to navigate programmatically, you often had to resort to these sort of hacky navigation links with some Boolean bindings, which quickly became completely unmanageable and brittle in any reasonably complex application. Tracking the source of navigation became a nightmare.
So how does Navigation Stack fix this?
Navigation Stack is the clean slate replacement. It's designed from the ground up to manage a true, explicit stack of views, much like UI Navigation Controller did. But critically, it offers first-class support for programmatic control through a binding to a navigation path.
Navigation path. That seems to be the key differentiator here. What is it?
It is. The navigation path is essentially a type-erased collection that holds the history of your navigation stack. It can store a sequence of different types of data that represent the different destinations pushed onto the stack.
So you bind the navigation stack to a state variable of type navigation path.
Exactly. You typically hold this navigation path in your view model or some coordinator object using @state. By doing this, you gain full control. You can spec the current stack by looking at the path. You can programmatically push new data onto the path, which triggers navigation to the corresponding view via .navigationDestination, or you can pop elements off the path to navigate backwards.
Just by manipulating that navigation path array like variable.
Just by manipulating the path variable. This finally gives us a reliable way to build features like deep linking, where you construct a specific path on app launch, or quickly resetting the entire navigation stack back to the root, or even inserting intermediate screens into the stack, things that were incredibly difficult or impossible to do reliably with the old navigation view.
That sounds much more robust. And how does data get passed to the destination screens in this model?
It remains clean and simple. You typically pass any required data directly via the destination view's initializer when you define the .navigationDestination for .destination.modifier that maps data types in your path to the actual views. It keeps state management nicely separate from the navigation mechanism itself.
Okay, so navigation stack for persistent stack-based navigation. What about presenting views temporarily, like modals?
Right, for temporary view presentation, we have three main presentation modifiers, each with slightly different characteristics and ideal use cases. Sheet, .fullScreenCover, and .popover.
Let's break those down. Sheet.
The cheat is probably the most common, the default modal presentation. It presents your content modally, usually covering only part of the underlying screen, especially on iPad, and critically, it's dismissible by default with a downward swipe gesture.
Good for what?
It's excellent for temporary focus tasks. Things like a quick input form, selecting an option, viewing secondary information, maybe a preferences panel, things that don't completely take over the user's context.
Okay, then full screen cover. That sounds more immersive.
Exactly.
Yeah.
As the name implies, full screen cover occupies the entire screen, completely obscuring the view underneath. It's designed for truly immersive flows where you want to eliminate the context of the previous screen entirely.
Use cases.
Think complex multi-step processes like user onboarding, sign-up or login flows, maybe dedicated editing modes or full-screen media viewers, situations where you want the user fully focused on the modal task. Historically, it was also a bit trickier to dismiss programmatically compared to a sheet, though that's improved.
And the last one, .popover. That feels more platform-specific, right?
It largely is. .popover is the standard presentation style for secondary content or controls on larger screens, primarily iPadOS and macOS. It typically appears as a small floating window anchored next to the button or element that triggered it.
And on iPhone.
On iPhone, due to the much smaller screen real estate, a top-over modifier generally defaults to behaving and looking just like a .sheet presentation, unless you specifically configure it otherwise.
Oh.
But semantically, it still represents that anchored secondary content idea.
And all three of these sheet, full screen cover, popover, they're typically triggered how?
They're usually triggered by binding the presentation modifier, like just showing sheet, to a Boolean @state variable.
Yeah.
Toggling that Boolean shows or hides the modal presentation. You can also bind them to optional identifiable state for presenting modals based on specific data items.
Okay, let's dive into some more advanced topics. The rise of SwiftUI really happened alongside the big evolution of structured concurrency in Swift itself, namely async await.
Yeah, the timing was pretty synergistic.
Now, we know everything UI related in SwiftUI has to happen on the main thread for safety. So how do we cleanly manage asynchronous work like long network fetches or complex data processing without blocking that main thread and making the UI stutter or freeze?
Right, that's fundamental. The basic building block here is the task. Introduced in Swift 5.5 alongside async await, the task type allows you to kick off a unit of asynchronous work. Async await itself lets you write that asynchronous code in a way that reads much more like simple synchronous code, which is a huge win for readability and maintainability.
No more pyramid of doom with completion handlers.
Exactly. No more callback hell. So you use task to create and start this asynchronous work. And as we discussed earlier, using the task view modifier is often the cleanest way to tie the lifecycle of this async work directly to the lifecycle of a view.
Because it handles cancellation automatically.
Because it handles cancellation automatically upon view disappearance. Super important.
But here's the crunch. Every time we need to update a SwiftUI property wrapper that drives the UI like at state, or more commonly, a at published property inside an observable object, we must be back on the main thread, right?
Absolutely must. It's a hard requirement. Trying to update UI-bound state from a background thread will, at best, cause unpredictable behavior and warnings, and at worst, crash your app.
So how do we ensure that happens reliably? Network fetch results, for instance, often return on background threads.
That is the crucial role of the @MainActor attribute. @MainActor is a global actor introduced with structured concurrency. It guarantees that any code annotated with it, whether it's an entire class, a specific function, or even a single property, will always execute exclusively on the main thread.
So I can just mark my view model class with @MainActor.
Yes. By marking your entire observable object view model class with @MainActor, you ensure that any method called on an instance of that view model or any update to its properties, including published ones, will automatically be dispatched back onto the main thread if needed.
So even if my network completion handler comes back on a background thread, calling a method on my @MainActor view model to process the result and update it at published property will safely hop back to the main thread first.
Correct. It handles the thread switching for you, preventing those dangerous data races and ensuring your UI updates are safe and smooth. It's a critical piece for safe concurrency in SwiftUI.
Okay, let's scale up the concurrency. What if I have a situation where I need to kick off, say, 5 different asynchronous network calls all at the same time, and then I need to wait until all of them have finished before I can process the combined results? How do I manage that kind of structure efficiently?
That exact scenario is what Task Group is designed for. A task group allows you to dynamically create and manage a collection of child tasks that can run concurrently.
Dynamically?
Yeah, you can add tasks to the group within a loop, for example, if you don't know exactly how many you'll need up front. The group then lets you easily await the completion of all the child tasks, collect their results, or handle errors in whatever order they finish, and ensures proper propagation of cancellation.
So it's perfect for that fire off end things, wait for all end things pattern.
Exactly. It's incredibly useful for parallelizing work and efficiently utilizing system resources when you have multiple independent async operations to perform.
Now, what about protecting shared data? If I have some kind of shared cache object or maybe an application-wide counter that multiple different concurrent tasks might try to read from and write to simultaneously, that sounds like a recipe for data races?
It absolutely is. Classic data race scenario. And that's where modern Swift offers another structured concurrency tool, the actor.
Actors, okay.
Actors are a special kind of reference type, like classes, but they are specifically designed to protect their internal mutable state in concurrent environments. They enforce mutual exclusion automatically.
Mutual exclusion, meaning?
Meaning they guarantee that only one task can access or modify the actor's internal state at any given time. If multiple tasks try to interact with the same actor instance concurrently, the actor system effectively serializes those accesses, ensuring that one operation completes fully before the next one begins on that actor state.
So it prevents threads from stepping on each other's toes when modifying shared data.
Precisely. If you were building, say, a shared in-memory cache for network responses, or maybe a thread-safe logging mechanism, defining that component as an actor would eliminate the possibility of data races without you having to manually manage locks or queues.
How do you interact with an actor's state then?
Any interaction with an actor's properties or methods from outside the actor itself must be done using await. This await keyword signals that you are potentially crossing an asynchronous boundary and that your task might need to suspend while waiting for access to the actor's protected state. It makes the potential for suspension explicit.
That structural guarantee sounds like it makes concurrent code vastly safer and easier to reason about than fiddling with locks.
It really does. Actors and task groups provide much safer, more composable ways to handle complex concurrency. And as the inherent reactivity we see everywhere in SwiftUI, this state-driven nature, it relies heavily on Combine, right? Apple's reactive programming framework. The connection seems deep.
Oh, absolutely. It's deeply integrated, even if sometimes hidden.
How exactly do those property wrappers we discussed at state object, at observed object, at environment object leverage Combine under the hood?
Well, they are essentially Combine subscribers. When an observable object uses the @published wrapper on one of its properties, as we said, @published automatically creates and exposes a Combine publisher for that property. Okay, the publisher emits values when the property changes.
Right. The SwiftUI property wrappers, at observed object, at state object, at environment object, automatically subscribe to the relevant object will change publisher that observable object provides, which is often triggered by its @published properties.
So when the @published property changes, its publisher emits.
The object will change publisher fires. The property wrapper receives that event because it's subscribed, and it then signals the SwiftUI runtime. Hey, the object this view depends on is about to change. You need to reevaluate the view. Combine acts as the underlying reactive transport layer that makes the whole automatic state synchronization mechanism work.
Got it. Combine is the plumbing. Okay, let's pivot to a very practical reality for many developers working on large existing applications, bridging the gap with UIKit.
Oh, yes, interoperability, crucial for gradual adoption.
If I have a really complex, maybe highly customized UIKit component, let's say a special UI search bar with a bunch of custom delegate methods, how do I get that working inside my nice new SwiftUI view hierarchy?
For embedding a UIKit view, UI view subclass, into SwiftUI, you use the UI view representable protocol. This protocol acts as a bridge or a wrapper.
Okay, UI view representable.
It requires you to implement a strict contract, primarily defined by 3 key methods or components, to manage the UIKit view's lifecycle and data flow.
Let's detail those 3 parts carefully because getting this right is crucial for successful integration.
Definitely. First, you have make UI view context. This function is called by SwiftUI only once during the initial creation of your representable view. Your job here is simply to instantiate the underlying UIKit view. So, create your UI search bar instance and perform any initial one-time setup that doesn't depend on changing state.
Create the view once. Got it. What's next?
Second is update UIView.context. This method is called every time SwiftUI detects that a piece of state your representable view depends on has changed. This could be triggered by changes in at state, at binding, at environment object, etc. that you use within your representable struct.
So this is where I configure the UIKit view based on the current SwiftUI state.
Exactly. If your SwiftUI view has a at state variable for the search placeholder text and that state changes, update UI will be called. Inside this method, you take the new placeholder text value from SwiftUI state and set it on the UView instance, your UI search bar. This method can be called very frequently, so it needs to be efficient. Only update what's necessary.
Okay, make for creation, update for syncing state to UIKit. Now the third piece, the coordinator. This one often seems to confuse people. What's its role?
The coordinator is the absolutely critical piece for bridging communication back from UIKit to SwiftUI. Many UIKit views, especially complex ones, rely on patterns like delegates or target action callbacks to report events or data changes. These patterns are inherently class-based and don't mesh well with SwiftUI's value type views.
So the coordinator acts as the delegate.
Precisely. The coordinator is typically a class that you define inside your UI view representable struct. You create an instance of it in another required method, makeCoordinator. This coordinator instance can then be set as the delegate or target for your UIKit view. For example, uview.delegate equals context.coordinator.
And when the UIKit view calls a delegate method.
When the UI search bar, for instance, calls a delegate method like searchbar.textDidChange, it's your coordinator instance that receives that callback. The coordinator then needs a way to communicate that change back to the SwiftUI world. This is usually done using a twat-gast into the representable struct, which the coordinator can access via the context or direct reference, or perhaps by calling a closure provided by the SwiftUI view.
So if I need the text typed into my UIKit search bar to update a SwiftUI at state variable, the flow is, user types UI search bar calls delegate method, coordinator receives callback. Coordinator updates the at binding Swift UI state changes Y SwiftUI view updates.
That's the exact mechanism. It completes the two-way data flow.
Yeah.
And the same core principles apply if you need to wrap a UIKit view controller, like UI image picker controller or maybe SSFR view controller. Using the sister protocol, UI view controller representable, it also has make UI view controller, update UI view controller, and often uses a coordinator.
Makes sense. What about the reverse scenario? Hosting shiny new SwiftUI code inside a large existing UIKit application, the gradual migration path.
For that, you use the UI hosting controller. This is a standard UIKit UI view controller subclass provided by the SwiftUI framework. Its sole purpose is to host a SwiftUI view hierarchy.
So I create my SwiftUI view.
You create your SwiftUI view structure, then you initialize a UI hosting controller with that root SwiftUI view, like UI hosting controller, my SwiftUI view. This hosting controller now behaves like any other UI view controller.
And I can push it onto a UIKit UI navigation controller stack.
Yep. You can push it onto an existing UI navigation controller, present it modally, or even embed its view property as a child view within a legacy UIKit view hierarchy. It's the essential bridge for bringing SwiftUI into existing projects incrementally, allowing developers to rewrite screens or features one by one without rewriting the entire app.
Fantastic. Okay, let's wrap up with some thoughts on maintainability and avoiding those sneaky performance pitfalls that can really degrade the user experience, even with SwiftUI's efficiencies.
Good call. I'd say the absolute cornerstone of maintainability in SwiftUI is composition. Break down every large, complex view into smaller, more specialized, and preferably reusable subviews.
Keep views small and focused.
Exactly. A view should ideally only manage a small slice of the UI and the state that's directly relevant to that slice. Avoid deep nesting of conditional if-else logic directly in the body. Try extracting complex conditional chunks into separate helper views or computed properties to keep the main body readable.
And architecture.
Absolutely. Strictly adhering to a sensible architecture pattern, MVVM, model view model, is very popular and fits well, is crucial. It ensures your data manipulation, business logic, and state management remain testable and clearly separated from the potentially volatile view structure. Keep logic out of your views.
Okay. And when things go wrong with layout or rendering, which can sometimes feel a bit like black magic in the declarative world, how do we debug effectively?
Use the visual tools. Xcode previews are your first line of defense for iterating quickly on layout and state changes. For runtime issues, the Debug View Hierarchy Inspector in Xcode is mandatory for understanding how SwiftUI actually composed your view tree and where things might be positioned unexpectedly.
Any quick tricks for layout debugging?
Yeah, don't be afraid to temporarily sprinkle .border or background modifiers with bright colors onto views whose frames or boundaries you're unsure about. It's a simple way to visually expose the actual space a view is occupying.
Good old border trick. And performance traps to avoid, beyond the don't compute in body rule.
Check your list implementations again. Are you definitely using list or lazy containers for potentially long content? Is your data reliably identifiable? And crucially, are you making smart use of equatable conformance or the equatable view wrapper for potentially expensive subviews?
Remind me how equatable helps performance.
If a parent view re-renders, SwiftUI normally reevaluates all its child views too. But if a child view struct conforms to the equatable protocol, meaning you can compare its relevant input properties, SwiftUI can be smarter. If the child view's inputs haven't actually changed since the last render and it's equatable, SwiftUI can skip re-rendering that entire child view subtree.
Ah, it diffs the view's inputs.
Exactly. It prevents unnecessary work. This can be a massive performance win, especially for complex child views that are frequently part of a larger parent view's updates. You can also achieve this sometimes by wrapping a view in equatable view, although direct conformance is often cleaner.
Fantastic. Okay, I think that roadmap from the core structural shift with value types through state management wrappers, rendering, concurrency, and bridging really gives the listener a complete picture of the framework's architecture.
Yeah, we moved from that old imperative manual update world of UIKit to this much more robust state-driven declarative system. It's powered by property wrappers, managing synchronization, and that efficient diffing, keeping things fast.
And hopefully you listening now know not just what the property wrappers are, but fundamentally why they exist, their roles in managing ownership, lifecycle, and synchronization. And crucially, how to choose the correct wrapper at state, at binding, at state object, at observed object, at environment object, based on the scope, ownership, and lifetime needs for the data in any project you tackle.
Knowing why is key to using them effectively.
Absolutely. So to leave you with a final thought to chew on, we've talked a lot about how SwiftUI helps enforce a single source of truth for local state, parent-child state, and even app-wide shared state using things like add-environment-object. But consider this. What happens when you introduce a complex external persistence layer? Something like core data or realm, or maybe even just a sophisticated network cache that needs to manage its own data lifecycle completely outside the SwiftUI view layer. How does maintaining that crucial single source of truth principle become exponentially more challenging?
Yeah, that's a big one.
It's no longer just about keeping two SwiftUI views in sync. Suddenly you need to synchronize the entire view tree, the state held within your view models, and the state managed by the persistent storage layer, and potentially incoming data from the network layer. How do you ensure transactional consistency and avoid conflicts across all these distinct complex systems simultaneously while still keeping the UI responsive? That integration, that's really the next level challenge in large-scale application architecture with SwiftUI.
It's a fantastic point. The complexity definitely scales dramatically once you involve serious persistence. Keeping everything consistent becomes the main game.
Something to think about. That's all the time we have for this deep dive. We'll catch you next time.